Hi everyone, so now we are going to start studying about multiplexers. So very interesting topic and very important as well. A lot of times questions will be asked from this particular topic in the interviews as well and in the gate examination as well. So what is a MUX? MUX is a many to one selector. That means there will be a lot of inputs but only one output. There would be a lot of inputs, only one output, and there will be select lines as well. So based on these select lines, one of the inputs will be selected and will be given to the output. Based on these select lines, one of the input will be selected and given to the output. Let's see how it will work. But before that, if the mux will be always in 2 to the power n into 1 form, like it could be 2 into 1 mux, it could be 4 into 1 mux, it could be 8 into 1 mux. What does this show? This is the number of input line and this is output. Number of input lines, output. So number of input lines are 2 to the power n. Number of input lines are 2 to the power n, and this n is the select line. N select lines will be there. So number of inputs are 2 to the power n, and output will be 1, and n select lines will be there. Okay, so let's write it down. If your mux is 2 to the power n into 1, so this shows number of inputs, this shows number of output, which will always be 1 only, and this n shows number of select lines, which you don't need to mug up, eventually you will remember it. Okay, let's study about 2 cross 1 mux. So there will be 2 input, 1 output, and 2 to the power 1 is there, so 1 select line will be there. Okay, what this select line will do? Now this select line can vary, it can take 0 value as well, it can take 1 value as well. So if select line is 0, then I0 will be taken out, and if select line is 1, then I1 will be taken out. Here 0 is written, no, so 0, I0 is taken out. If select line is 1, then I1 is taken out. So select line can vary, its value. S is 0, then I0 will be taken out at output, and if S is 1, I1 will be taken out. So how I can write my Y expression? If S is not there, then my output is I0, and if S is there, my output is I1. Do you remember in min terms and max term, when we were studying SOP and POS, we saw this kind of truth table where output was 0 1 0 1 0, and in there somewhere I mentioned output is C. So how did we write? If A bar is not there, B bar is not there, then output is C. So similarly, if S is not there, then output will be I0, and if S is there, output will be I1. So can you design it? Very easily I can design it. How will I design it? S, and then I0 is there. This is S, this is I0, this is again S only, and this is I1. Both will be taken out and will be fed to the OR gate, and this will be the output Y. So this is your combination circuit, which is not that important. Wait a second. Yeah, so I was saying which is not that important. We will solve a problem regarding this, but later on we will solve it. On a block level it is important. So we will solve MUX problem on the block level only, not on the circuit level, on the block level. That if S is 0, then I0 will come. If S is 1, then I1 will come. What about 4 cross 1 MUX? What do you think? What about 4 cross 1 MUX? It will have 2 select line, because this is 4 cross 1 MUX. 4 will be input, 1 will be output, and select lines will be 2, because they did 2 to the power 2. So these can also vary. These can be 0 0, these can be 0 1, these can be 1 0, and these can be 1 1. If these two are 0 0, then output will be I0. If these two are 0 1, that means decimal equivalent is 1, so output will be I1. If these two are 1 0, that means decimal equivalent is 2. Decimal equivalent is 2, so output will be I2. And if decimal equivalent is 3, so output will be I3. So generally, if S1 S0 is written and nothing is mentioned, they are not mentioning whether it is MSB or this is LSB. So S1 will be taken as MSB and S0 will be taken as LSB. Although they should mention it, but if nothing is mentioned, then S1 will be taken as MSB and S0 will be taken as LSB, because it is having 1. So let's take it as MSB and S0 as LSB. Okay, and these are I0, I1, I2, I3. By default, you would know that I0 means 0 0, I1 means 0 1, I2 means 1 0, and I3 means 1 1. And these can interchange, like I3 can be written anywhere, I0 can be written anywhere. These are the inputs, so it can be written anywhere. I3 can be written here, I1 can be written down, I2 can be written up, I0 can be somewhere in middle. So these can be written anywhere. Just you need to know that if my select line input is 0 0, I will take I0. If my select line input is 0 1, I will take I1. If my select line input is 1 0, I will take I2. If my select line input is 1 1, I will take I3. So if S1 is not there and S0 is not there, my output will be I0. If S1 is not there and S0 is there, my output is I1. If S1 is there, S0 is not there, my output is I2. If S1 is there, S0 is there, my output is I3. So this is the final expression of Y. Okay. Do the same for 8 cross 1 mux. So 8 input will be there, 1 output will be there, and select lines will be 3. So if all 3 are 0, my output will be I0. This will be taken as MSB and this will be taken as LSB. What will be the decimal equivalent of this? That would be 1. So it would be I1, it would be I2, it would be I3, it would be I4, it would be I5, this will give I6 and this will give I7. You can write down the Y expression. So if S2 bar, S1 bar and S0 bar, then I0 will be my output. If S2 bar, S1 bar, S0, then I1, and in that manner it will keep on going. You can write it down. If S2 is there, S1 is there, S0 is there, my output will be I7. Okay. Now tell me one thing. If I am saying that I have a function f, which has the variable s1 and s2. I have a function f which has the variable s1 and s0. This is some function. I am naming this function as x. Okay, I am naming this function as x. So this is my function. So can I write down it in this manner, that y is equals to m0 I0 plus m1 I1 plus m2 I2 plus m3 I3, where m0, m1, m3, m2 and m3 are the minterms of x. Look, my function x is there which has two variables s1, s0. If s1, s0 both are 0, that means it is minterm m0. If it is 0 1, or you can, if it is 0 1, then it is minterm m1. If it is 1 0, it is minterm m2, and if it is 1 1, it is minterm m3. The condition is my function x should have only two variables which are s1, s0. Now if I am saying that my function x is having s1, s0 and some other variable, let's just say which is I2, I am telling some other variable is also there. This is my function f. Then I cannot write this is my m0. Then I cannot write this is my m0, because my m0 will be 0 0 0, and it's not necessary that your I2 is 0. Are you getting this point? Like it will depend on s1, s0 and I2. But if it is only depending on s1 and s0, then I certainly know that these two will be 0 0, and that will belong to m0. 0 1 will belong to m1, 1 0 will belong to m2, and 1 1 will belong to m3. If my function is the function of, if my boolean expression is the function of s1 and s0, so then only I can write it down. So this is a very important point which I mentioned, that my function is of s1 and s0, then only I can write it down. Okay, we will use it later on. As of now we will not use it, but later on this expression will be used. Similarly here as well I can write down y in this manner, m0 I0 plus m1 I1 plus m2 I2, in that manner till m7 I7, right? Okay, we will use it later on. Let's see some questions now, because this is a very easy topic. The typical part will come, but probably in the next video. Okay, here easy part will be coming. So all these are easy questions. Just write down the minterms of y. So how will you write down? So if b is not there and c is not there, that means both are 0, then a will be coming out. If b is there and if b is not there, if this is 0 and this is 1, then what is the decimal equivalent? 1. So I1 will be coming out, that is 0. Plus, if b is there and c is not there, that means what is the decimal equivalent? Decimal equivalent is 2. Then a bar will be coming out. Plus, if b and c both are there, then it would be a1 will be coming out. So the expression is b bar c bar a plus B C bar A bar plus B C. Okay, this is the expression. Now let's write it in the better manner. That is BC plus A B bar C bar plus A bar B C bar. So y would be equals to, we need to find the min terms. So I need to introduce A here as well. How will I introduce? ABC plus A bar BC. I hope you remember it. A B bar C bar plus A bar B C bar. Okay. So this min term is M7. This min term is 0 1 1 M3. This min term is 1 0 0. This is M4 plus this min term is 0 1 0. This is M2. 7 3 4 1 and 2. Yeah. So the min terms are 2 3 4 7. So you couldn't solve this question as M0 I0 M1 I1 plus M2 I2 plus M3 I3. If you have solved in this manner, then what will be your M0? That would be B bar C bar, and what is your I0? That is A plus B bar C 0 plus B C bar A bar plus B C 1. So now you cannot say that, sir, this is my min term M2. No. Now M1, M2, M3, M4, M5, M6, M7 and M0 will be defined as per this, because this is your final output, which is having the variable of A, B and C. Your final output is not having the variable A, B, BC only. If it was having variable BC only, then you could have said these will be my min terms. But your final min terms will be different. Are you getting this point? Now let's just say I will copy this question. Okay. Yeah, it has been copied. So let's remove it. Let's remove everything. Now this is the new question, and output will not have now A, because A is gone. So output will be function of B and C only. Now you need to write down the min terms of output. So let's write down by conventional method. That would be simply, if B is not there and C is not there, then 1 is coming. Plus, if then 1 is coming, so I will multiply 1 as well. Plus, if B is not there and C is there, then 0 will come. Plus, if B is there and C is not there, that means 2, 0 will come. Plus, if B is there and C is there, 1 will come. So output will be B bar C bar plus BC. So this will, what this will be? This will be M0 and this will be M3. So your Y is having 0 and 3. You can directly see I0 is coming and I3 is coming. Why it is so? Because Y can be equals to M0 I0 plus M1 I1 plus M2 I2 plus M3 I3. So this is 0. This is also 0. So in the answer only I0 will come and I3 will come. So in the answer M0 plus M3 will come. In the next lecture we will use it. Somewhere we are going to use it. Okay, that's why I am writing it. But make sure that all the variables are used as a select line. All the variables are used as the select line. Here I am writing it. All the variables used as select line. So this is the thing. All the output variables are used as a select line. So then only you can apply this method. Okay. Let's go to the next one. Minimize expression. So just write down the expression by your conventional method. So what will be the select line? Select line will be BC. B into C, BC. So what will be your output Y? If B and C are not there, if BC is not there, basically, I can assume this as X, right? If X is not there, my output will be A. Oh, sorry. If look at it. If X is not there, my output will be what? I0, which is 1. If X is there, my output will be A. Or I can write BC bar into 1 plus BC into A. So X bar plus XA could be written as X bar plus A. So that is the minimized expression of Y. or it could be written as A plus B bar plus C bar. Are you getting this point? I hope you must have understood that BC bar is not there, then BC is not there, that means BC bar, then 1 would come. If BC is there, then A would come. So X bar plus XA can be written as X bar plus A. So that would be the answer, which is BC bar plus A, or it could be written as A plus B bar plus C bar. So that is the final answer. Let's move to the next one. What would be the minimized expression of output? So here S0 is fixed at 0. Say yes or no. If S0 is fixed at 0, A can have the value of 0 and 1. So how will you write output Y? Output Y. That would be written as, if A is not coming, then what is the input? 0 0. If A is not there, that means input is 0 0. You will pick B. And if A is coming, so what is the input? Input is 1 0, because this is S1. You notice here, this is S1. So if A is 1 and S0 is fixed at 0, so this decimal equivalent of this is 2. So you will pick I2, that is 1. That's it, this is the answer. And A plus A bar B can be written as A plus, this is A plus A bar B. So output will be A plus B. This is your Y. Did you understand this point? What I did here? S0 is fixed at 0. You cannot change S0. A can change. A can have 0 value. A can have 1 value as well. What is the decimal equivalent of this? 0. What is the decimal equivalent of this? 2. So if A is not there, that means A bar is there, then B would come. If A is there, then I2 will come, that is 1. So A into 1. So A plus A bar B, that is A plus B. Okay. So write down the minimized expression of this. This would be AB. This would be B XOR C. VCC means 1. Okay. And this is ground. This would be D only. Right. Minterms of Y you need to find. So it would be a lengthy problem, but it would be easy only. If D and C are not there, then AB would come. If D is not there and C is there, that is 0 1. 0 1 means this will come, that is B XOR C. Plus, if D is there and C is not there, then 1 would come, 1. And if both are there, D and C both are there, then 0 will come. So this is the final expression. It can be written as A B C bar D bar plus D bar C. It can be written as B bar C plus B C bar plus C bar D, and this DC is 0 only. So now I can write it as AB C bar D bar plus this would be B bar C D bar, right? B bar C D bar, because C into C will be C only, and here C and C bar will be multiplied, which will be becoming 0. What I am saying, C bar and C will be multiplied. D bar C into B C bar, C and C bar will be multiplied. It will become 0, and it would be C bar D. So I need to write down them in terms. So how will I write down them in terms? 1 1 0 0. What this will have? This is 0 1 0, right? 0 1 0. A can have value 0 as well. A can have the value 1 as well. What about this? This is 0 1. So 0 1 0 1 0 1. AB can have a value 0 0 0 1 1 0 1 1. This is how we write down the minterms. What is being repeated? 1 1 0 0 1 1 0 1. I guess nothing is being repeated. So this is 12. From here what we are getting? 1 2 1 2 4 8 10. What about this? This is 1. What about this? This is 5. What about this? This is 1 2 4 8 9, and this is 12 and 13, right? So what all are the minterms? 1 2 1 2 5 9 12 5 9 10 12 13. So 4 here, 2 here, 6 7, 4 3 6 7. Okay. So I hope you must have understood. Let's see it again. D bar C bar AB, D bar C B XOR C, D C bar 1, and DC both are coming, then 0. then this would be the expression B bar C D bar, and this will become 0, and this would be C bar D, A B C bar D bar, 1 1 0 0, 0 0 1 0 1 0 1 0. What about this 0 0 0 1? Okay, yeah, same, yeah, it is fine. 0 1 0 1 1 0 0 1 1 1 0 1. This would become 13, this would become 9, this would become 5, this would become 1, this is 2, this is 10, and this is 12. So that's how we write down the min terms. Let's go to the next one. So before moving on to the next topic, I will tell something very interesting. In any combinational circuits, you see, no, in any combinational circuit, not just talking about this MUX, any combinational circuits. So there will be some input bits, there will be some output bits, right? I know there will be some inputs, there will be some output bits as well. There could be select lines as well. Here there was select lines, there could be select lines as well. But something 3 are constant. What is that? There will be a supply, there will be ground, and there will be a enable button. You know what is supply? +5, ground is 0. What is this enable button? So if direct enable is written, direct EN is written, that means it is active high enable. What do you mean by active high enable? That if EN is equals to 1, then your IC is working. IC means this is your combination circuit. So combination circuit is working perfectly, working the way it was working. If EN is 1, it is working perfectly. If EN is 0, this is not working. That's it. Combination circuit is not working. Basically your output is 0 or 1. Your output is fixed. It could be 0, it could be 1. Based on your combination circuit, it could be a fixed output, it could be 0 as well, it could be 1 as well. But if enable bit is 0, then your combination circuit is not working. If your enable bit is 1, that means combination circuit is working. What about active low enable? That means if your enable circuit is 0, if your enable button is 0, then your combination circuit is working, and if your enable button is 1, then your combination circuit is not working. Active low enable, that means you need to give low at the input. Now this seems like okay, let EN is 0, then my circuit is working. If EN is 1, then my circuit is not working. And here EN bar is written. So basically if EN bar is 1, or you can say EN bar is 1, or you can wait a second. Basically in place of EN bar, if you apply 0, in place of EN bar if you apply 0, then it is working, and in place of EN bar if you apply 1, then it is not working. It is written, it is active low enable. So now people get confused that sir, here bar is there and here one more bubble is there, so I can cancel out both of them. No, you do not cancel out actually. This is a way of representing. If one of them is having bar, or there is a bubble, or like simply EN bar is written, or both of them could also be there. Are you getting this point? They could write EN and only a bar, only a bubble. They could write only bar. You could get to know that, you have to get to know that it is active low enable. And they could have written EN bar and bubble both together. Then also you need to get to know that it is active low enable only. That means if EN bar is equals to 0, then it is working. And if EN bar is equals to 1, then it is not working. Okay, let's see a problem, it will be more clear to you. So here EN is written, here EN is written. Okay, that means this is a enable button, active low enable, sorry, active high enable, active high enable. This is active high enable. So what will be your output? Let's make a truth table first. So here there is A as well, EN as well, and Y. So if A is 0, forget about EN. If A is 0, what you should expect as output? I0. And if A is 1, what you should expect as output? I1. But this will work only if EN is 1. If EN is 0, no matter whatever that is there at the input, output will be 0. There will be no output. If EN is 0, no matter whatever that is there at the input, output will always be 0. It will not look at select line, it will not look at select line, it will not look at this I0 I1 input. If En is 0, En means En is equals to C. If your C is 0, better I should write C here. If C is 0, then this circuit is not working. So how you can write down the output? If A is not there, then answer will be 1. Plus if A is there, then answer will be B. With the condition that your C should be 1. Your C should be 1. This should be 1. Then only this will be the output. This will be the output dot C. So this is the final expression. So your final expression will be, this can be expressed A bar plus AB. A bar plus AB can be written as A bar plus B dot C. So your final expression becomes A bar C plus BC. Are you getting this point? If C is 1, then only this circuit will work. So if C you are putting 1, then only this will be your output. If you are putting C equals to 0, then output will be 0, because C is 0. So 0 multiplied with anything will be 0 only. So you need to put C equals to 1. And we are expressing it in terms of SOP. This is product term, right? So if this is product term, then C is the normal form and C bar would be the complemented form. Now what do you understand by this? Here En bar is written. Here En bar is written. What they could have done? They could have put a bubble here as well. So again we need to understand this is active low enable. This is what? Active low enable. So if C is equals to 0, then it is perfectly working. If C is equals to 1, then it is not working. We will see this one first. We will see this symbol, or they could have written bubble here, or they could have only put a bubble. Mostly this will be written. There is very high chance that this will be written. They can put a bubble here as well. They can frame this thing. That bubble here is there and En is there. Or they can only frame the En bar and no bubble. En bar plus bubble, En bar plus bubble, and En plus bubble. These three conditions can be there. So whenever you see bubble, that means it is active low, and whenever you see bar, that means it is active low. If both are together, then also it is active low. Like people can think that, sir, En bar is there plus bubble is also there, so bar and bubble can get cancel out, so it is active high. No. In GATE examination, 2 to 3 times the question has come. Even in GATE 2024 as well, the question came, and people were saying that En bar is there and 0 is there. So both should cancel each other and it should work as enable button. No, it doesn't happen like that. En bar is there plus bubble is there, still it is considered as En bar only. So you need to take care of this. Okay. That means this is our active low input. So if C is 0, then our output will be working, and if C is 1, then output will not be working. Okay. So without making the truth table, let's write down the final answer. What that would be? If A is not coming, if A is 0, then output will be 1, and if A is 1, then output will be B. A bar into 1 plus A into B, with the condition that your C should be 0. C should be 0. So if C should be 0, that means I will write C bar here, because if C is 0, then C bar would become 1, and C bar would become 1, and 1 is multiplied with this expression. That means this will be the output. If C is 0, then your circuit is working. If C is 0, then your circuit is working. So C 0 in min terms, how will you write it? C bar. So A bar plus AB dot C bar. And here also you can put, if you put C equals to 0, what you will get? A bar plus AB, C equals to 0, so C bar will be 1. So this is what you get, and this is what you want. If C is 0, your circuit should be working. So here you will write C bar. Okay, and how it can be reduced? A bar plus B dot C bar. So it would be A bar C bar plus B C bar. Okay, so that's the final expression. Okay, so that is the meaning of enable button. We will use it again and again. So here I have explained it. So active high enable, active low enable. Okay, let's use MUX as a universal gate. So using the MUX, you can make all the basic gates, universal gates, and arithmetic gates. So let's try making NOT gate. What you need to make? NOT gate. Y is equals to A bar you need to make. How will you make it? Y is equals to A bar. That means with A bar you need 1 and with A you need 0. If A bar is coming, then what you will pick? I naught. Basically, you write your output y as A bar. If A bar is coming, I will pick I naught. If A is coming, I will pick I1. So if A is coming, you will pick I1. That's it. This is your inverter. If you need to make buffer, how will you make it? Buffer. Let's write down buffer gate. Try making it on your own. I will directly write down the answer. Because here you just need to use your brain. If you are not using your brain, then digital electronics will not come to you. Because digital electronics is the aptitude of electronics engineering. This is all about aptitude. Okay. What do you think? What should be the value of I0 and I1? I0 should be 0 and I1 should be 1. Because why? If A bar is not coming, if A bar is coming, that means if A is not coming, so I can say if A bar is there, I will pick 0. If A is there, I will pick 1. So y is equals to A. So this is your buffer gate. So can you just remember that in inverter, I0 will be 1 and I1 will be 0. Basically 0 is 1 and 1 is 0. So opposite is there, no? So it is inverter. And here 0 is 0 and 1 is 1. So same is there, so it is a buffer. So kind of you can remember it, or it will take 2 seconds to get to know it is a inverter, right? Because if A is 0, A bar into 1. So basically it is inverter only. A into 0, sorry, A bar into 0 plus A into 1. So this is a buffer. Or you can just see, okay, 1 is there or 0 is there, that means this is an inverter, this is a buffer. AND gate you need to make. Y is equals to AB. So if A is coming, I need B. And if A bar is coming, I need nothing. If A is coming, I need B. If A bar is coming, I do not need anything. So Y is equals to AB, right? What about Y is equals to A plus B? So if A is coming, I need 1. But if A bar is coming, what do I need? I don't know that. Because there is B as well. So somehow in the expression, that is Y is equals to A plus B, I need to introduce A bar. How I can introduce it? I can write B into A plus A bar, because A plus A bar is 1. So here there is B into 1 only. So A plus A bar, because I want to introduce A bar. So A plus AB plus A bar B. So from here you are getting A into 1 plus B, that will be A only. So A plus A bar B. So A plus A bar B is A plus B only. So now you get to know that if A is coming, I need 1. And if A bar is coming, I need B. That's it. So this is your OR gate. Similarly, what about this? What is this? AB bar. So it can be written as A bar plus B bar. You know about A bar, but you do not know about A. So I need to introduce A somehow. So there I have introduced A. So this is A bar plus A B bar plus A bar B bar. So A bar you can take common from these two. A bar you can take common from these two. So you will get A bar plus A B bar. So if A bar is coming, you need 1. And if A is coming, you need B bar. Right? Let's think about NOR gate. Later on I will have to copy it. So just keep it copied. So yeah. Let's talk about NOR gate. So NOR gate can be written as A bar dot B bar. I will always try to write it in SOP form. When I am solving the problem of MUX, I will write it in SOP form. Why so? Because answer are in SOP form only, no? A bar dot I naught, A dot I1. Answer are in SOP form. So I will write it in SOP form only. So if A bar is coming, that means I need B bar. And if A is coming, I need 0. Okay? So in the same manner we are proceeding. Nothing different we are doing. What about XOR gate? So for XOR gate, directly we can see here. If A is coming, I need B bar. And if A bar is coming, I need B. If A bar is coming, I need B. And if A is coming, I need B bar. So this is your XOR gate. What about XNOR gate? This is your XNOR gate. So if A is not coming, I would need B bar. And if A is coming, I would need B. Okay. If A is coming, I would need B. So here the answer is A bar, B bar plus AB. But one thing is there, like we have mentioned B bar here, mentioned B bar here. In this as well, we have mentioned B bar, right? Here we did not mention. Here we mentioned B bar. So how will you get this B bar? So for B bar as well, you can use a MUX. Like the user can say that I have only the literals, that is A and B. I only have A and B literals. I do not have their bar. So you can make bar as well, no? Simply use the MUX as an inverter. How do you use MUX as an inverter? I naught I1. This is your I naught. This is your I1. So I naught should be 1 and I naught should be 0. And this is your B. What you will get from here? B bar. So you get this B bar and then you connect it here and this will work. Okay. The similar thing you can do here. So making NOR gate will take two 2x1 MUX. Making NAND gate will take two 2x1 MUX. Like in the examination or in the interview, if they are asking make NAND gate using 2x1 MUX. So first you will make this B bar and then you will connect this B bar here and then you can say, sir, this is my final design. Like you will make it more beautiful. Basically you will pick this one here and you get the output B bar, directly you will connect it here and then you can say, sir, this is my final expression. Okay. Now implement the following function using only MUX, and MUX you need to use, that is 2x1 MUX. Okay. And the expression is, two expressions are there. This is first question and this is second question. In those questions there are two more questions, that is first you need to take A as a select line and then you need to take B as a select line. In these questions as well, it could be given that take B as a select line and make all these gates. Like you need to take B as a select line. Let's just say this question is there and you need to take B as a select line. How will you solve it? Select line should be B. Here directly I took select line to be A. Anything I would have taken it. So if my select line is B, so that's my question now, and this is I naught, this is I1, and this will be my output Y. This will be my output Y. So if B bar is coming, I would need A bar, and if B is coming, I would need 0. So that would be my answer. That's it. Select line could be anything. Here also I could have make it, right? If B is coming, I would need A bar. So here I would, sorry, if B bar is coming, I would need A bar. If B bar is coming, I would need A. So here I would have picked A. Here I would have put A bar, and this A would be replaced with B. Okay, very easy. Now this is the question. What you need to implement? A bar B. So I am implementing A bar B. A bar B using A as a select line. And now I only need to use MUX only. I only need to use MUX because they are saying using only MUX. I don't have any inverter or anything like that. So if this is I naught, this is I1, what I need to make? A bar B. So if A bar is coming, I would need B, and if A is coming, I would need 0. So this is my output, A bar B, right? Now let's implement the same thing using select line as B. Select line as B. So select line is B now. This is I naught and this is I1. So if B is coming, I need A bar. If B is coming, I need A bar. And if B bar is coming, I would need A. So is that the correct answer? No. Here did you use any inverter here? No. You had A available, you had B available, certainly 0 will be available. But here you have B available, here you do not have A bar available. So you need to make A bar. How will you make A bar? Very simple. Because I have A available with me. I have A available with me. This I will pick I naught, this I will pick I1, this I will pick 1, this I will pick 0. So if A bar is there, I will get 1. If A is there, I will get 0. So A will not come, only A bar will come. So this is the A bar. From here you get A bar, and from here B bar is coming, you get 0, and B is coming, then you get A bar. So this is the answer, B A bar, or you can say A bar B. So only using our what do we say, MUX only we have designed it. But here I had to use A as a select line. This I had to use. Okay, there was no other option left. I had to use A as a select line. So if I need to make A bar B, then what is a better design for me? This is the better design for me, because here I have to use two MUXes. And how do I decide which is the better design for me? I need A bar. In my design I need A bar. So which select line I should use, A or B? Select line I should use as A. Why so? Because select line has the capability of giving bar as well and the simple form as well. Are you getting my question? What I am saying? So your manager is saying, your manager is asking you, go design A bar B, go design a function A bar B, and try to use minimum number of mux, because if mux are more, then cost will be more and power consumption will also be more. So try to use minimum number of mux, and what you need to design, you need to design A bar B. So what should be your select line, A or B? You will pick select line as A, because the select line has the capability that first it will give you A bar with I0 and then it will give you A with I1. If I had picked B, so it would give me B bar and B. But I do not need B bar. What I need? I need A bar. If I do B bar and B, I am only left with A. I am not having A bar. But actually I need A bar. So from here directly I am getting, no, so only one mux, using only one mux I have implemented it, but here I need to use two muxes. Okay, so these kind of important points will come in next lecture. There we will see it broadly, but here I am giving you a feel. The target is to solve the problems here, but just a kind of feel I am giving so that you could connect the next lecture. So that is very important actually. The next lecture is very important for your interview perspective as well and for your this gate examination perspective as well. Next, what you need to implement, A plus B bar. So you need to implement A plus B bar. So let's use A as a select line. If I use A as a select line, I have the problem. Why I have the problem if I am using A as a select line? Because I know what will come with A, but I do not know what will come with B bar. So I have to solve it. A plus B bar, what I can add? A plus A bar. So A plus AB bar plus A bar B bar. This is A plus A bar B bar. So now I know with A what will come? 1 will come. This is I0, this is I1. So with A 1 will come, and with A bar B bar will come. B bar will come. So now you have to make B bar. So what we can do, we can put this analysis somewhere here for now, and now I need to make B bar. So B bar should be made. So I will use B here, right? This is your I0, this is your I1. I will put opposite, one I0 as 1 and I1 as 0. So what I will get? B bar and then this. Okay. And if I had to use B as a select line initially, so A plus B bar only I am making. So Y is equals to A plus B bar. I know what should come with B bar, but I do not know what should come with B. So this I had to do, right? So it would be AB plus B bar, right? Very easy. So if B is there, this is I0 I1. So if B bar is there, this should be 1. If B is there, this should be A. So that's it. B bar into 1, B into A. This is your output Y. So that's the final expression. This is the final design. So in this one, you only need to use 1 mux, and here you need to use 2 mux. Why is that so? Because here you needed B bar, which mux has the capability if you use it as a select line. If you use B as a select line, mux has the capability of giving you B bar. So that's why here you use one. Here you choose only 1 mux, but here you need to use 2 muxes, right? Let's solve this question. Now you will say that, sir, you said that only one output can be there for mux, but here there are 2 outputs. There is only one output. This output is just simply complemented. Nothing else is there. Output is F1 only, but this is just a complemented output. Okay. So what would be your F1? What do you think? F1 will be C will go here and C will also go here. So if C is not there, you will get 0. F1, let's write down F1. If C is not there, you will get 0. And if C is there, you will get D. If C is there, you will get D. So F1 is CD. So what this would be? CD bar. Very easy. this would be CD bar, and that is going here. This would be CD bar. This is your CD. What about this one? What about F2? F2. If C is not there, you will get D bar, and if C is there, you will get 0. So what is your F2? If C is not there, in the examination you will write it very quickly. You will not do this thing. If C is not there, you will get D bar. So this is your actually this is going here. So this is your C bar, D bar. And what about F2 bar? F2 bar, or this can be written as C plus D bar whole bar, right? C plus D whole bar. So F2 bar would be C plus D only. F2 is C plus D whole bar. So F2 bar would be C plus D, right? Now what about output Y? If A is not there and B is not there, then CD. If this is your MSB, right? So if A is not there and B is there, that means it is 0, 1. So it will take C bar, D bar. Sorry, CD bar, it is CD bar. Plus, if A is there and B is not there, basically it is 1, 0. So it will pick C bar, D bar. And plus, if A, B both are there, then it will pick C plus D. Okay. So better let's write down the output somewhat above. This is CD bar, CD whole bar. So I can write it as C bar plus D bar, right? This is CD whole bar. It can be written as C bar plus D bar. This is CD whole bar. It can be written as C bar plus D bar, right? So Y would be equals to A bar, B bar, CD plus A bar, B, C bar plus A bar, B, D bar plus A, B bar, C bar, D bar plus ABC plus ABD. Okay. So minterms would be 0, 0, 1, 1 because A is MSB. 0, 1, 0, 0, 0, 1, 0, 1. 0, 1 and D bar is 0. 0, 1, D bar is 0. So this should be 0, this could be 1 as well. Because here C is not there, so C can take both of the values. Here D was not there, D can take both of the values. What about the next one? That is G1, sorry. It would be 1, 0, 0, 0. What about this ABC? ABC is 1, 1, 1. D can have value 0, D can have value 1 as well. What about ABD? ABD. So 1, 1, 0, 1 and 1, 1, 1, 1. Right? ABD. 1, 1, 0, 1, 1, 1, 1, 1. So this got cancelled. And what about others? Anything is getting cancelled? No, let's check out. This is 3. This is 4. This is 5. This 4 are being repeated. This is 6. This is what? 13. Right? This is what? 8. This is 14 and this is 15. So what are the minterms you are having? 3, 4, 5, 6. 3, 4, 5, 6. 8, 13, 14 and 15. So these are the minterms you are having. Right? Okay, well and good. Let's see some delay based problem. Okay, now we are going to see delay based problem. So MUX has a switching delay of 1 microsecond. Switching delay of 1 microsecond. Comment on V naught. Although 4 option will be mentioned, but here why should we mention the option? We should have the concept. What is the select line here? Select line is directly connected to the output. So this is your V naught. So let's try writing V naught. What will be V naught? V naught will be, if V naught is not there, then it would take 1, and if V naught is there, it would take 0. So your V naught is equals to V naught bar. Do you see anything here? What is that? Remember chapter 1? Output is connected back to the input. This is your V naught. I should not extend it. There is no meaning of that. So V naught goes in, you get V naught bar. Then V naught bar goes in, you get V naught. So what is this? This is A stable multi vibrator. Multi vibrator. Only one inverter is there. 1, 3, 5, 7, 9. These number of inverter could be there, right? A stable multi vibrator. What else you can call it? Ring oscillator. What else you can call it? Pulse wave generator also you can call it. Pulse wave generator. So initial value of V naught I don't know. Let's just say if initial value of V naught was 0. So next value would be 1. Next value would be 0. Next value would be 1, 0. So this is a pulse wave generator. Okay. And if we started from here, this has the delay of 1 microsecond. So for 1 microsecond it would be 0. Then for 1 microsecond it would be 1. Basically you will start from here. You are starting from here. Okay. So this was 0. This 0 will come here. This 0 will come here. It will give you 1 after 1 microsecond. So this will take 1 microsecond. Now this 1 will come here. It will give you 0 after 1 microsecond. So this will take 1 microsecond. 1 microsecond. So all these windows are 1 microsecond. So what is the time period? What is the time period? Time period is 1 by 2 into total delay. What is the total delay? That is 1 micro. So that is, sorry, time period. Why I am putting 1 by? Time period is 2 microsecond. 2 into total delay. 2 into total delay is 1 microsecond. If you remember this, we have already studied in chapter 1. That's why I am dealing it quickly. So answer is 2 microsecond. So what is the frequency? That is 1 by 2 megahertz. So 0.5 megahertz. This is frequency of oscillations. So if someone is asking you, this particular question is given and find the frequency of oscillation, answer would be 0.5 megahertz. Let's solve this question. This is your output Y. Y is going here. What you will get? If Y is 1, if Y is coming, then 1 would be there. If Y is not there, then 0 would be there. So output will be Y only. Select line is Y, output will be Y only. So what do you think? What is this? Buffer. What about this? This Y is going here. If Y is not coming, that means if Y bar is there, then 1 will be multiplied. If Y is there, then 0 will be multiplied. So this will be your Y bar. So with Y select line, you are getting Y bar. What is this? This is a NOT gate or inverter, I should write. This is an inverter, right? What about this? This Y bar is there. You can see I1 is connected to 1, I0 is connected to 0. So 0 is connected to 0, 1 is connected to 1. So rightly I can say this is buffer. Here I could have said 1 is connected to 0, 0 is connected to 1, inverter. 1 is connected to 1, 0 is connected to 0, buffer. So what is this circuit? This circuit is simply, first there is a buffer, then there is an inverter, then there is a buffer. So odd number of inverters are there in the loop. In the loop there are odd numbers of inverter. If there are odd numbers of inverter, what does it mean? That is, it is a stable multivibrator or ring oscillator, you can say a stable multivibrator. And what all are the delay? 5, 7 and 8. So what would be your answer? What do you think? What will be the frequency of oscillations? Frequency of oscillation will be 1 by 2 into total delay. Total delay is, never forget this 2. A lot of time people forget this 2. They will just add up the delay 1 by that delay. That they will do. But you need to remember 0 will come for that much time, 1 will come for that much time. Then again 0 will come for that much time, 1 will come for that much time. Okay, so that you need to remember. So 12 1 by this total delay is 20 nano, right? 20 nano. Yeah, 20 nano. So answer would be 1 by 40 nano. 1 by 40 nano can be written as 1000 mega by 40. 10 to the power 9 would go upward, so 10 to the power 3. So it would be 25 megahertz, right? It would be 25 megahertz. So that is the correct answer. So these kind of questions can come in your examination. This has come in gate examination. Okay, this has also come in gate examination only. This has also come in gate examination. Comment on why. Tell the frequency of oscillations. Tell whether it is a stable multivibrator or not. So comment on why. So let's start commenting. Y will come directly here. Y will come here. This is your Y. Output is connected here, and this is your Y bar, right? And S is fixed at 1. S is fixed at 1. So what will be your output Y? S is fixed at 1, so you only need to care about Y bar. So 1 into Y bar. So Y is equals to Y bar. But how much time it will take to give the output? First, this comes at t equals to 0. Let's just say Y is equals to 0 at t equals to 0. So after 5 nanoseconds, this will be 1. After 5 nanoseconds, this will be 1. And after 20 more nanoseconds, it will become bar of that. That means it will become, directly it will come, sorry. Basically, at t equals to 0, Y is equals to 0. At t equals to 0, Y is equals to 0. After 5 nanoseconds, this has become 1. After 20 more nanoseconds, this 1 will come out. Basically, whatever that is there, Y is equals to I1. The thing is, Y is equals to I1. Y is equals to I1. And I1 is Y bar. So if Y is equals to 0, after 5 nanoseconds, this will be 1. And after 20 more nanoseconds, this 1 will come out. Now this 1 is there at 25 nanoseconds. Now at 30 nanoseconds, this will become 0. At 30 nanoseconds, because 25 plus 5, 30 nanoseconds, this will become 0. And after 20 more nanoseconds, this 0 will come out. So basically it would be 15 nanoseconds. So for 15 nanoseconds, there is 0. And for 25 nanoseconds, there is 0. And for 25 nanoseconds, there is 1. Then again, this cycle will keep on being repeated. So basically, you need to calculate the total delay in reaching at the output. 5 nanosecond plus 20 nanosecond, that would be 25 nanosecond. From here you are going, let's remove it off. So 5 nanosecond this will take and 20 nanosecond this will take. So this is 25 nanosecond. And this is 25 nanosecond. So this is a pulse wave generator. What is the frequency of oscillation? That would be 1 by 50 nanosecond. And it can be written as 1000 mega by 50. That would be 20 megahertz. Now let's copy this question again. I can frame one more question from here. Yeah, so if I change the question in this manner, I have changed this question in this manner. This particular circuitry is given. You need to comment on Y again. So what will be your Y? S is equals to 1. S is fixed. S is fixed. So it will look at only I1, right? And what is I1? I1 is Y only. So Y is equals to Y. Basically this is a buffer, right? Y is equals to Y. This is a buffer. This is your Y. And the same way it will keep on going. So this is a buffer. So what kind of multivibrator is that? There is no oscillations, right? Because always Y will be equals to Y only. Always Y will be equals to Y only. So no oscillations is there. So it cannot be a stable multivibrator. Because like I am asking you this question because I know a lot of people would have forgot what is astable, what is monostable and what is bistable. Because people forget it. That's why I give the analogy there. If you remember by analogy, you will remember it for a longer time. Otherwise, you will forget it. So it is not a stable multivibrator. In a stable multivibrator, there is no stable state 1 0 1 0 1 0. So what is that? Monostable or bistable? What is monostable? Monostable means there is only one stable state. So if it is 1, for a momentary time it can be 0, then again it will be 1. And what is bistable? If it is 1, there will be 2 stable states. Bistable means 2 stable states. If it is 1, it will be 1 only. But if you apply some trigger and if you make it 0, it will always be 0. So let's just say if my Y was initially 1, so it will always be 1. But if I apply some trigger here, and make it 0, then it will always be 0. And again if I apply some trigger, let's just say I break it and put 0 here, so it will be 0, always 0. And if I again apply the trigger, it will be again 1. So if you have forgot the concept, then I would recommend you to go and study astable multivibrator again, multivibrators again. So this is your bistable multivibrator. There are 2 stable states. Y is bistable multivibrator. So you will be getting confused in monostable and bistable. So in digital electronics, you will never see monostable multivibrator. For momentary time, there is no unstable state. Whether it is 1 then it will be 0. Then if you give a trigger, it can be 1. Okay, so this is a bistable multivibrator. Okay, let's see the next question. Next question is also very interesting. Propagation delay question is there. 2 questions we will solve. So propagation delay of XOR gate, AND gate and multiplexer in the circuit shown are 4 nanosecond, 2 nanosecond and 1 nanosecond. So XOR gate 4 nanosecond. Okay, AND gate 2 nanosecond. 2 nano, 2 nano, 2 nano and MUX is 1 nano. MUX is 1 nano. All inputs PQ RST are available simultaneously. That means all the inputs are available at a given time, that is t equals to 0. All the inputs are available at t equals to 0 and held constant. The maximum propagation delay of the circuit is. So what is the select line? How to solve these kind of problems? Select line is t. Select line is t. So now t could be 0 as well and t could be 1 as well. If t was 0, if t was 0, if t was 0, it would have taken this value. And to get, and if t was 0, if t was 0, it would have taken this value and this value. Now this value will take here, it will take 4 nanosecond. So t has to wait 4 nanosecond to get this output, at least 4 nanosecond. Are you getting this point? Look, t is 0, t is 0, t is 0. So now after 4 nanosecond something will come here. Before that there is nothing. So after 4 nanosecond, Q and R will be XOR and will give you something here. So 4 nanosecond and MUX will take time of 1 nanosecond to give the output. So after 5 nanosecond you will receive some output here. And after 7 nanosecond you will receive something here. But you do not need to look this one. You need to look here. So here you can see that if t is 0, if my t is 0, then this input will be available after 2 nanosecond only. If my t is 0, this input will be available after 2 nanosecond. Because from here P will come, here Q will come, and after 2 nanosecond it will be available. So just as it sees the input, it will give that to the output. So 2 nanosecond plus 1 nanosecond, it will take 3 nanosecond. Are you understanding this point or not? First put t equals to 0. If I am putting t equals to 0, then if I look at this MUX and then I need to look at this MUX. So always look at the final MUX. So this final MUX, what this final MUX is saying, that if your t is equals to 0, then I need to look at this. And when this will be stable, this input is stable after 2 nanosecond. So if this input is stable after 2 nanosecond, so after 2 nanosecond this MUX has the capability of giving the output. So 2 nanosecond and MUX will take 1 nanosecond to give the output. So answer will be taken out at 3 nanosecond only. Although this bit will become stable after 7 nanosecond, but answer I can take after 3 nanosecond only. Because if t is equals to 0, t will not look at this, t will only look at this. So if t is equals to 0, your delay is coming out to be 3 nanosecond. So is this should be the answer? No, wait a second, because you did not take the condition of t is equals to 1. Let's take the condition of t is equals to 1 now. This was 1 nanosecond and this was 2 nanosecond. Okay, so if t is equals to 1, t is equals to 1. So I will always look at the final MUX. So this will wait for this one. T is equals to 1, so it has to wait for this input to come. Now after how much time this input will come? Here t is equals to 1, right? Here t is equals to 1. So it will look at this. So after 2 nanosecond this will become, and after 3 nanosecond this will be the output. Look, if t is equals to 1, it will look at this. So after 2 nanosecond this input will be stable, and after 2 nanosecond MUX has the capability of giving the output, but it will take 1 nanosecond more to give the output. So 2 nanosecond plus 1 nanosecond, so this will be 3 nanosecond. And what about this input? Because you need to look at AND gate now. This is your AND gate. So this input is available at 3 nanosecond, and this input is available at 2 nanosecond only. This input is available at 2 nanosecond only. So when the gate will give the output, when this AND gate will give the output, after 3 nanosecond or 2 nanosecond? Basically this gate was there, this input was available at 2 nanosecond and this input came after 3 nanosecond. So output will depend on both of the inputs, no? So it will give output after 3 nanosecond. So this AND gate has the capability of giving output after 3 nanosecond, but it will take 2 more nanosecond. So this has also had the delay of 2 nanosecond. So after 3 nanosecond this input is stable, plus 2 more nanoseconds. So this output will be stable at 5 nanosecond. Now at 5 nanosecond, this MUX has the capability of giving the output. At 5 nanosecond, this MUX has the capability of giving the output. So how much time it will take? 1 nanosecond more it will take. So output will be stable at 6 nanosecond. So for t is equals to 0 and t is equals to 1, both you need to check. So you just need to make the path, that's it. For t is equals to 1, delay will be 6 nanosecond. Now if you go to some user and you tell him that, sir, the delay of my circuit is 3 nanosecond. You go to the user and tell him that, sir, delay of this, the circuit I have designed, that is 3 nanosecond, and he put t equals to 1. So how much delay he will get? 6 nanosecond. Then he will fire you, right? Your job will be lost. So delay is defined always as the maximum delay. That, sir, maximum delay could be 6 nanosecond. Now delay you can get 3 nanosecond as well or 6 nanosecond, but maximum is 6 nanosecond. So if they are asking what is the delay of the circuit, then always you need to pick the maximum one. So delay of the circuit is 6 nanosecond. Now you can go to the user and you can tell him that, sir, the delay of my circuit is 6 nanosecond. So he will apply the input 0. He can get the output in 3 nanosecond only. So he will be happy because delay is 6 nanosecond that he don't want, but still some delay is there, and you give him the specification that 6 nanosecond is delay, and he is getting output in 3 nanosecond only. So he is happy, and now he applies the input 1. He gets the output after 6 nanosecond. Then he is also happy because you said that the delay is 6 nanosecond. Okay. So when delay is there, you always need to pick the maximum one. So what is the maximum one? Maximum one is 6 nanosecond. So answer would be 6 nanosecond. Okay. Let's remove these off which are not required. So in that manner, you need to solve t equals to 0 and t equals to 1. Let's see the next question which you need to solve on your own. Okay. So now let's solve this question. So these data are given, delay of all the gates are mentioned, and MUX delay is also mentioned. The same question is there, you need to find the maximum delay at the output. So the same way I will approach. First I will put t equals to 0. So if I put t equals to 0, so if I put t equals to 0 here, what I will get here? 1 I will get. After 1 nanosecond, this input 1 will be stable after 1 nanosecond, right? And this will be stable at t equals to 0 only. So this 0 will look for this one, like, but this 1 will look for this. Now you need to look at this and this. So this 0, this is t equals to 0, is looking for this. This will be stable after 2 nanosecond, and this will be stable after 3.5 nanosecond. And since this is looking for this only, so it has to wait for 3.5 nanosecond, because after 3.5 nanosecond only this will be stable. So before that, MUX doesn't have the capability of giving the output. So 3.5 nanosecond plus 1.5 nanosecond. So delay for this is 5 nanosecond. Are you getting this point? This input is stable at 1 nanosecond, right? So from 1 nanosecond, it is waiting that when this input becomes stable. After 1 nanosecond, this is there. This guy is standing there and he is waiting. Just as it becomes stable, my MUX will have the capability of giving the output. So it is becoming stable after 3.5 nanosecond. So it has become stable now. Now MUX has the capability of giving the output, so it will take 1.5 nanosecond more. So 3.5 nano plus 1.5, 5 nanosecond is the total delay. For t is equals to 0. Let's check for t equals to 1. And before going there, let's just say if this delay was 4 nanosecond. If this delay was 4 nanosecond, then tell me what will be the delay at the output. If this delay was 4 nanosecond, then what will be the delay at the output for condition t equals to 0? What would be the answer? 5.5 nanosecond, right? Because this input will become stable after 4 nanosecond. So this input has already become stable, but MUX will say that I do not even know whether I want to give this as output or this as output. So after 4 nanosecond, the MUX will get to know that my S0 is 1. That means I need to give this output. So after 4 nanosecond, MUX has the capability of giving the output. Now MUX can make a decision that I need to give this output. So after how many seconds? 4 nanoseconds. So 4 nanosecond plus 1.5 nanosecond, that would be 5.5 nanosecond. If this delay was 4 nanosecond, but here this question is easy. The delay is 1 nanosecond only. Okay. So delay kind of problems are basic aptitude problem only. You just need to think that when the device has the capability of giving the output. That's it. Okay. Let's check the other case. 2, 2, 2 1, these were given. Okay, now t is equals to 1. Now if t is equals to 1, so this input 1 will become stable at t equals to 0 only, right? And this will become 0 at t equals to 1 nanosecond, at t equals to 1 nanosecond. So this has to look here. I will look at the final one. This has to look here. Now after how much time this will become stable, that we need to know. So p will come here as it is. Now can I say that this what is this gate? This NOR gate has the capability of giving the output after 2 nanosecond. Can I say this thing? No, I cannot say, because the output of this NOR gate will depend on this input as well. So when this input becomes stable, that I get to know, that I need to know now. So if this is 1, that means it will look here. So this becomes stable after 1 nanosecond. So after 1 nanosecond, MUX has the capability of giving the output. Now MUX will take 1.5 nanosecond more. So after 2.5 nanosecond, this will be stable. So now after 2.5 nanosecond, this NOR gate has the capability of giving the output. So 2.5 plus 2. So this will be 4.5 nanosecond. Right? This will be 4.5 nanosecond. So after 4.5, this point is 2.5 plus 2, 4.5 nanosecond. So now this will look at this input only. So after 4.5 nanosecond, this has the capability of giving the output. After 4.5 nanosecond, this MUX has the capability of giving the output. So that will be 4.5 plus 1.5. So t is equals to 1. So delay would be 4.5 plus 1.5. That would be 6 nanosecond. So what will be the answer? This would be the answer. That's it. Okay. So now our this part is completed, and in the next lecture onwards we will move towards this implementing lower level MUX from higher level MUX, or implementing higher level MUX from low level MUX. So that we are going to see in the next video. So that will be a very interesting video as well, and very important as well. Okay. So in MUX everything is important. These kind of questions are also important. So let's meet you in the next video. There we see about implementing more MUX from some MUX only. Okay.